And so this lecture will be about broad brushes, how the CMB is measured, why that's hard, a few words about the landscape of current experiments, and then I'm hoping to take the rest of the lecture to just talk about sort of relevant physical quantities we're trying to learn about with the CMB at the moment and how we learn about them with the CMB. So the Hubble parameter today, H0, and properties of the neutrinos, so how many of them and how massive they are. And the reason I'm focusing on these parameters is because there's a lot of controversy around them, and so I think it can be useful to know exactly how they are measured from the CMB and other probes so that you can form your own opinion and your own assessment of current measurements. So yeah, again, the hope for today is that by the end, you'll have some idea of how CMB maps are made, of how the Hubble parameter is measured from the CMB, and how we learned about neutrinos from the CMB. So, okay, CMB measurements. What goes on? What is required for you to be able to produce a map of the cosmic microwave background? The first thing is you have to be able to see the cosmic microwave background. And so here you have two options. Either you're in outer space and then you're in a satellite, you don't need to worry about the atmosphere, or you're from the ground and then you need to worry about the atmosphere. And so what's being shown here is the curve of the atmospheric transmission, so how much of the light goes through the atmosphere as a function of the frequency at which you are observing. And you can see three different curves here. The one in red here is what you might expect from a location on the ground. Blue is the Atacama Plateau in Chile, so a very high altitude desert, very dry. And green is the South Pole, so Antarctica. And so again, a place that's actually very dry. And what you can see is, so what you want in this plot is you want the transmission as close to 1 as possible, so that as much of the CMB light can go through the atmosphere and reach you. And what you can see is that when you go from someplace like on the ground to someplace in high altitude or in the South Pole, is that you get very big differences in your atmospheric transmission. So if you want to observe the CMB, it helps to be at high altitude. It helps to have very dry air. And the reason for this is because the water molecules inside the air and the atmosphere are a big part of the absorption. And of course, if you can get all the way above the atmosphere, that's even better. The other thing you can see from the ground is that sort of regardless of where you are, there are some frequency ranges, frequency bands, where basically the CMB will be absorbed. And so you can't really efficiently observe on these windows. And so that might explain to you why, a lot of the CMB frequency bands, when you hear about CMB maps at different frequencies, why the frequencies are chosen in this way. So one is you have to put your frequencies where you can. So you will typically see CMB frequencies around 90 or 100 gigahertz, CMB frequencies around 150 gigahertz, and then above. And so this curve of the transmission, if you're a ground-based experiment, informs how you will choose your frequency bands. Another thing that will inform how you choose your frequency bands is what are the foregrounds you want to focus on removing as best as possible. And another thing you have to think about, which is not on this plot, is that there are emission lines from various molecules at different frequencies in here. And so you may want to design your frequency bands to avoid these emission lines if they're not interesting to you, or you may want your frequency band to have these emission lines if you want to map them. Okay, so that part was the atmosphere, how to see the CMB through the atmosphere or from space directly. And then the next step, assuming that those CMB photons have been able to reach, all the way towards you, either by crossing the atmosphere or because you're in space, how do you take this CMB light and convert it into a CMB map is the next step. And I should say I'm not an expert on CMB instrumentation, and so this list here is sort of my schematic understanding of how you make a CMB map from CMB experiments. But I think I'm hoping it will still be helpful. So one important thing to keep in mind is you're trying to measure the temperature of that radiation. So you're observing the intensity of that light in a certain frequency band, and you're trying to know how much light you're seeing, what's the intensity or what's the temperature. And so an analogy that I gave, I think, in the first lecture is using one of those infrared thermometers where you press a button, there's a sensor that counts how much infrared light in a certain band is being received and converts that to a temperature. And so it's kind of what you're doing. You're a telescope that collects that light, not in the infrared, but in the microwave, and tries to convert the intensity into a temperature. And again, to remind you of the scale of the challenge here, we've talked about how the CMB mean temperature is 3 Kelvin, so 3 degrees above absolute zero. The typical CMB temperature fluctuations are of order 100 microkelvin. Some of the effects that I talked to you about yesterday, for example, this kinematic SZ or other secondary anisotropies, are roughly microkelvin in size. And if instead you are interested in measuring the B-mode polarization, the signals are even smaller. And so a number you might have in mind is nanokelvin. So 10 to the minus 9 Kelvin. And you can compare this with room temperature, which is 300 Kelvin. So you can see that there's many orders of magnitude between the temperature of where you are and the temperature of the radiation you're trying to observe. And of course, everything around you that's at 300 Kelvin is going to be emitting light at 300 Kelvin, which would overwhelm your measurement if you're not being careful. So that's the first thing to keep in mind. And again, this analogy of you are sitting inside of your oven with your little infrared thermometer trying to measure the temperature of the freezer that's open on the other side of the room, except the problem here is a lot harder. Okay, and so you're trying to measure these very small temperature fluctuation by observing the CMB light. And so you have the CMB light that arrives to you. And so the first thing that occurs in your chain is optics. So much like any other telescope in optical or other frequencies, you're trying to focus that light so that you can image it onto your focal plane, so that when you take an image with different pixels on your focal plane, you have an image on the sky. So there's sort of, you'll see two types of CMB experiments with two types of optics. You will see telescopes with large apertures that typically use mirrors and then lenses. And you'll see telescopes with smaller apertures that use only lenses. So refractive telescopes with just lenses and reflective telescopes with also a mirror. The reason for these two choices has to do with several factors. One of them is beam. And beam is the term that's being used in radio transmissions or radio astronomy for basically the resolution of your experiment. In optical astronomy, this is what we call the point spread function. So if I take a point source in the sky, how big will it look on my focal plane? That's a measurement of the beam. And for the beam, size matters because a lot of CMB experiments are actually diffraction limited. And so you can compute the typical width of your beam. So if I, as a function of angle, if I put a point source here at this position and I ask how much intensity am I going to see when the source was actually a Dirac delta, I will typically see an extended image. If you've designed your experiments to make your life easy, if you're lucky, your beam might just be a Gaussian with a certain width. And that width is typically of order the diffraction limit, which is a function of the wavelength of your light, so for us, a couple millimeters, and the aperture of your telescope. And so if you want to reach arc-minute resolution, which is needed for a lot of the secondary anisotropies I told you about, you will typically need mirrors of about 6 meters or larger to get that diffraction limited beam. And so if you want to have an aperture of about 6 meters in diameter, you are going to need mirrors as opposed to lenses. Another factor is that so beam is a consideration that might drive you towards larger apertures and typically mirrors. But another factor is how simple your beam is and how well you can control it. And this will typically drive you towards simpler designs with fewer complicated reflections. And so this might drive you towards refractive telescopes with just circular lenses all the way. Okay, so you've used your optics, you've put a mirror, or you've put lenses, and your CMB photons are being focused onto your focal plane. How do you count those photons? How do you measure the intensity of light? The next step at these frequencies is to try to couple this light to an antenna. And so your detector is actually an antenna, so you can think of it as just you know, a metal stick that's going to capture the radio signal. And so you need to couple the light to that antenna. There's various ways of doing this. This can be done with lenslets, which are small lenses placed on each pixel. This can be achieved with other devices that are called orthomode couplers. So this is not really my area of expertise, but at the end of the day, the light is placed onto a pixel. And the pixel of the focal plane will typically basically have two different antennas in two different directions. And so each of these antennas is going to capture the light in the corresponding polarization. So when your electromagnetic wave arrives and the electric field oscillates vertically, this antenna is going to capture, to be coupled to that light. And if the light is polarized horizontally, that antenna will capture it. And so you're basically making maps of the polarized intensity in each point of the sky in the two axes of polarization. And by measuring the difference between these polarization, you measure the polarization Q and U, the Stokes parameters we talked about. And by summing the intensity in both directions, you will get the intensity. So this is how CMB pixels actually work. Generically, there are roughly two antennas with two different directions, and you capture the light in these two directions. Now, okay, you had that light from the CMB that reached this antenna and made the electrons oscillate, changed the voltage in that antenna. How do you measure this? And the way this is typically done is by coupling this antenna with basically a very sensitive thermometer. And so current CMB experiments are bolometers, meaning for all the light within the frequency band that reaches this antenna, that light will just be converted into heat, and the temperature, the corresponding temperature of your system will be measured. So you need a very sensitive thermometer coupled to that antenna to be able to measure the very small changes in temperature. And the way this is currently done is with something called transition edge superconductors or sensors. And the idea with those transition edge sensors is that they are a component who's a superconductor, but instead of keeping it either in the superconducting regime at very low temperature, where the resistance is very small, or keeping it at the high temperature regime where it's just a normal conductor, you keep it right on the edge of superconductivity. And the reason for doing this is that as the temperature varies, you can ask how the resistance of your superconductor changes. And typically, you will find something like this. And so there is a range of temperature here around the edge of superconductivity. So at low temperature, you are a superconductor. At high temperature, you are a normal conductor. But if you can keep your system right on this edge here, what happens is that a very small change in temperature will result in a very large change in resistance. And so that's how you get extremely sensitive thermometers, basically. There's another approach to transition edge sensors, which is called KIDS, kinetic inductance devices. And I'm really not an expert in these things, so I won't tell you more about it. But qualitatively, the feature to keep in mind is what you have is a very sensitive thermometer, something that will convert changes in the temperature of your bolometer into changes in the resistance, which you can then read out. Typically, just so you have heard the word SQUID, superconductive quantum interference devices, this is a system that comes typically after this thermometer to amplify the difference in the resistance, and so the difference in the signals. And so these are other sophisticated devices that basically just allow you to amplify the signal while keeping a very low noise. Yes?
So when people try to, because it will be a really so in principle, when people try to construct different CMB experiments, are, for example, if you are looking for an experiment that has a really good angular resolution, will that translate to the quality of the other things that you're trying to measure, or is it?
Right. Yeah, so that's a very good question. And so all the choices you make here in the design and how you build your telescope will affect the performance of the maps you get at the end. And so the way all these choices are made usually is you have your science goals. So for your experiment, there are some parameters that you want to measure really well to a given precision. And then you can trace how those scientific requirements flow down to requirements on your instrument. And so the design decisions here are all made in order to optimize some science cases. And of course, as always, I think in engineering, you have trade-offs. And so you can make a very big telescope to have a very high resolution, but that might result in challenges in the shape of your beam, which may be an issue for other science cases. And this is why a number of experiments actually now are sort of hybrid with two different types of telescopes. Large aperture ones that give a very good resolution and help you map the small scales, and small aperture ones with a much broader beam, but a very well-controlled one, which lets you map the large scales very accurately. Thanks.
Sorry, I have a question.
Mm-hmm.
So these parallel lasers, which is like all the time, and a lot of instruments right now have these screens have this problem that they are super conductive versions, right? So they have this problem that the operating point, which they acquire the data, is not split.
Mm.
It's kind of changed.
Mm-hmm.
The transfer function of the so this problem is called SLAC sham.
Mm.
Know if how this other instrument solve this problem?
Mm. Right, it's a really good question. I suspect, yeah, from your experience working on Cubic, you probably know a lot more than I do on these instrumental challenges. So I don't actually know the answer to your question, but I'd be interested. So if you find out, let me know. Thanks. Any other questions on this? Yes.
Can you explain again how the polarization is measured?
Right. And so if you remember from the session on CMB polarization, you take your electric field and you can decompose it into the two components of the electric field, for example, in some X and Y directions. And your Stokes parameters here are related to the intensity in various directions. And so what we typically call intensity is the average of EX squared plus EY squared. And your Q parameter might be EX squared minus EY squared. And the U parameter that tells you about polarization at 45 degrees, if I call these axes, A and B. So this defines your Stokes parameters. And so you can clearly see that, this bolometer here is going to let you measure EY squared, and this one will measure EX squared. And so from this sensor, you will directly get I and Q. And then if you want to get U, you have two options. Either there's a nearby sensor that's oriented differently, or as you scan, the sky will rotate with respect to your sensor. And in that case, you will get the other polarization. Okay. And in terms of, so again, I'm not an expert in CMB instrumentation, but in terms of the current challenges in instrumentation, my understanding is the following. that right now the detector technology is good enough in terms of the noise being low enough such that your sensors are not the noise in your sensor is determined by the incident photons on your sensor. So this is called the photon noise limit regime. So it's the regime in which your noise is determined by how many photons fall onto your sensor. And these photons are CMB photons as well as other photons from, for example, the atmosphere or other sources. And so if you want to improve your sensitivity in your CMB map, you do not need to make a better sensor. You need to either reduce the amount of photons on your sensors that are not from the CMB, or you need to build more sensors. And this way you have more photon collection power. And so this is, to my understanding, the regime we're in right now. The next step I wanted to talk about sort of qualitatively is how we make a map. And so for most optical telescopes, for example, you might be used to, what you do is you point your telescope where you want to see, you expose for a certain amount of time, and that's your image. For CMB experiments, you can't really do this. And the reason, again, has to do with the scale of the problem. You're trying to measure extremely, extremely small fluctuations of temperature from one point to the other. But of course, if you just stare at one point in the sky, what you'll find is that over time, the temperature of your whole system is evolving by amounts which are much larger than the temperature fluctuation. And so there's sort of two things that save you. But the main one is that you expect the CMB to vary on fairly small scales, so degree scales and lower. And you expect the temperature variations of your system due to, the sun moves in the sky or any changes in temperature in your cryogenics to occur on slow timescales. And so what you can do is you can scan quickly the sky. And as you scan quickly the sky, anything that varies very fast with time will have to be due to CMB fluctuations. And anything that varies slow will be just fluctuations of the temperature of your system. And so this is why CMB experiments don't just stare at one point of the sky. Instead, they scan very fast. And as you scan, you get something that we call the time-ordered data or the time-ordered information. And so from each of these receiver antenna, from each of these bolometers, you will get a signal as a function of time. So this little pixel will see many different points across the sky over time, and you get the time stream for the reading from these pixels. Then what you do is you filter out anything that varies slowly. These are fluctuations in temperature of your system, and you keep the things that vary fast. So that's why CMB experiments scan, and that's what this time-ordered information is. But the next step is you have scanned the sky repeatedly, and all of your pixels in your focal plane have seen different points of the sky, and you've scanned this way. How do you convert that into a map? To my knowledge right now, there's sort of two main approaches to doing this in practice. One is called filter and bin. So you filter your time-ordered data. At any moment in time, you know where your telescope is pointing. And so if you want, you can give yourself a pixelated map of the sky, and you know at any given time which pixel every sensor is looking at. And so you can add this information to that pixel and average the noise down. And the other approach is called the maximum likelihood map making. And that one basically just writes a full likelihood for the time-ordered data, given your knowledge of your pointing and your knowledge of the noise. And based on all this data, all the time-ordered information from every single sensor, you can then solve for what is the maximum likelihood or the maximum a posteriori map of the sky. So I think this is all I wanted to say about how to convert the CMB photons from the sky into a CMB map, in part because this is mostly the extent of my knowledge of it. But if there's any questions on this, I'm happy to try to answer. Yep. Sorry, can you speak louder so I can hear? Right, so I think the question is, are we sure that at the end of the day our CMB map is not affected by variations in the temperature of our system? Right. And I think there's several ways we can avoid this. But typically, you know, every point of the sky will be visited many, many times by many, many different sensors. And you have repeated observations over many, many days and nights. And so the idea is that hopefully the temperature fluctuations of your system will not be correlated from, you know, one day to the next or 1 hour to the next, et cetera. Whereas the CMB will always be, or at least the microwave sky will always be the same. So this is something that helps you, is repeated observations with, you know, you don't scan one position on the sky only once. Depending on what statistical properties you want for your map, another thing that can help you is called cross-linking. Not every experiment chooses to do this, but for example, the scanning strategy for the Chilean experiments is typically at constant elevation, and you scan in azimuth. And what happens is, as you do this, the sky might be setting or rising. And so effectively, if you scan like this when a patch of sky is rising, or if you scan like that once it's setting, you will be scanning at a different angle with respect to the sky. And so now you have sort of cross patterns of how you've scanned, which helps you further resolve some of these issues. Yeah, thanks for the question. Yes? Variation in the temperature. Yes, and actually this is something where you might know more than I do about this with all your experimental work. But basically, yeah, you're trying to measure fluctuations in temperatures that are extremely small, microkelvin or even nanokelvin, and you are inside of a cryostat, which is inside of a room at room temperature at 300 Kelvin. And so if you're trying to measure fluctuations at the micro or nanokelvin level, it's very hard for any system you build to be stable at these levels of temperature. And so typically things will evolve over time. And that's where it helps that those fluctuations are smaller than the speed at which you're scanning. And in fact, that's how you choose your scanning speed. Cool, thank you. All right, and so I just wanted to mention a few experiments. And these are by no means all the experiments. There are some of the ones I know. And in fact, I know there are people in the room who have been working on many other CMB experiments. So I think after talking about these, maybe I'll ask you in the room to just say a few words about your experiment, if that's okay. And so I have analyzed data from the Atacama Cosmology Telescope, which is located in Chile, and concluded all its observations about a couple years ago. So a lot of the data analysis from this telescope have been released. The DR6 data release 6 cosmological parameters and maps are publicly available for anyone to download online. So this is a 6-meter telescope, and so a high angular resolution, about 1.4 arc-minutes beam that has mapped about half of the sky, most of the southern sky with declination below about 10 or 15. Simon's Observatory is the successor to the Atacama Cosmology Telescope. It will be a hybrid design with a combination of large aperture telescope with similar aperture to ACT, but much higher data throughput because the focal plane is now much larger thanks to a different design. And small aperture refracting telescopes, which will be focusing on the large scales and things like primordial B modes. Our colleagues in Antarctica and at the South Pole have really powerful telescopes. The South Pole telescope, which has a resolution and sensitivity comparable to ACT and has produced really amazing cosmological parameters even a few weeks ago. And next to the South Pole telescope is the BICEP and Keck experiments. And so these are, again, small aperture telescopes, refracting telescopes, so lenses, which are meant to map the large scales with very clean systematics. And so now I know that there's people in the room working on other CMB experiments. Maybe can I ask the cubic people to tell us more about the cubic instrument? And maybe, yeah, let's wait for the microphone.
Well, cubic is like, it's also a CMB experiment that tries to measure the beam mode of the CMB, but it has a very special structure because it combines interferometry and bolometry. So you have like this array of antennas at the beginning of the window where the photons enter, and also it has a Stokes polarimeter before that models the polarization and also avoids the cross polarization from the rest of the instrument. And well, this interferometry that characterize cubic is very important because it can control the systematics error of the instrument, so you can be aware of the self effects that can induce the instrument. So that's very good. But well, it also combines this test and squid for the chain detection, and well.
No, just the same. I mean, it's the same idea as Lucas say, and also what you explained. But as Lucas say, it incorporates this horn array, which makes this interferometry. So that's why the beam is quite complicated. It's not like similar to a PCF. And we are trying now. We are in the calibration phase, trying to understand the response of the instrument. The instrument is placed in Argentina, in Salta, which is very near to Atacama also. So the conditions in the skies are pretty similar too. But we are trying to understand now the response of the instrument, and we are dealing with several things. One of them is the flag jams, which is a project that Lucas works a lot, that arise from the squids. Yeah, trying how to see how to make for example, the map making when you have this very complicated beam. Yeah, I think that's it. It's mostly. It's an international collaboration that involves mostly France, Italy, and some parts of US and also Ireland, but mostly France, Italy, well, in Argentina.
Great. And can you tell us just in one word, what's the key science goal for Cubic? What are you trying to measure?
Well, the big goal of the instrument is to measure the primordial beam modes, but otherwise it could also help to make best measurements of the foregrounds in order to make better models for the component separation. We are still researching, but due to this beam, which is frequency dependent, maybe we can create the components of the foregrounds during the map making, but we are working on that.
Great, thanks for that. Thanks so much for telling us about Cubic. And I realized I also wanted to tell you about Lightbird, which is an upcoming satellite whose goal is going to be to measure the large scales in the CMB temperature and polarization with very good precision and control of foregrounds and systematics. And so one thing I'm really excited about from Lightbird is updated measurements of the optical depth through reionization, which is an important parameter that has degeneracy with a lot of things in cosmology. And the other one is the search for the primordial beam modes on the larger scales. Any other people in the room working on other CMB experiments who would like to tell us about them? Okay, so if not, thank you. This is all I was planning to tell you on how the CMB is measured and the landscape of ongoing and upcoming experiments. And I would like now to switch gear to tell you about how the Hubble parameter is measured from the cosmic microwave background. And the reason I decided to focus on this parameter is you surely have heard about this Hubble tension and the fact that measurements or predictions from the Hubble parameter based on the CMB appear to be in disagreement with local measurements from supernovae calibrated with Cepheids. And so I thought it could be useful if I told you how H0 is measured from the CMB so that you have a sense for what goes into those tensions and what you can or cannot trust. So let's see. This might be best done on the board. So how to measure the Hubble parameter today, H0, from the CMB. Thank you. And so the first step is something we've talked about before, is that the CMB tells you all about all the energy densities of all the components in the universe, except for dark energy. So how to go from CMB to all the rho I for every I that's not the cosmological constant. And so, okay, so the first thing we've measured from the CMB is its temperature. And if you know that the photons are a black body distribution and you tell me the temperature in the photons, well, then I know everything there is to know about these photons. And so in particular, I know about their energy density. So I know the energy density in photons today. And because I know how temperatures just redshift as 1 over A, I know the photon energy density at all redshifts. Okay. How do I learn about the other energy densities? Does anyone remember how to learn about, matter or baryons from the CMB? From the acoustic peaks, yes. And what specifically?
The baryon.
Right, and so which property of the acoustic peaks tells us about the baryon abundance? Right, yeah, so thank you both. The odd versus even peak heights tell you about the ratio of rho baryon to rho photon, but since you know rho photon, it tells you about rho baryons. And again, you know how this redshifts. You know that the energy density in pressureless matter goes down as 1 over A cubed. And so you know this at all redshifts again. What are the other energy densities out there in the universe that I would like to know? Dark matter, yes. How do I learn about rho dark matter or rho matter? The height of the first peak, yes. And so you might remember that radiation driving potential envelope. So if you remember, modes that enter the horizon in matter era versus radiation era get a different amount of amplitude. And this was why, when you look at the CMB power spectrum, there was this envelope here with a certain amplification, and the CMB power spectrum looked like this. And so by looking exactly at which scale this amplification arrives, this tells you about what are the Fourier modes that cross the horizon right at matter radiation equality, which tells you about rho matter over rho radiation. And since, again, you know rho radiation from the CMB temperature, this tells you about rho total matter. Okay, what are the other components in the universe that have an energy density? Curvature. Okay, so curvature, that's a really good point. And so this reminds me that I need to qualify the title of this section to be flat lambda CDM. Right, I heard neutrinos as well. Neutrinos. And so curvature, the challenge there is, again, that geometric degeneracies that I mentioned. And so I'm going to assume that rho kappa equals 0, but that's an assumption. That's not inferred in any way. And somebody said neutrinos. Yes. How do you learn about the energy density in neutrinos, or how would you know what that is? I guess I didn't really explain that part. So there's two ways in which that matters. So one way you can get it is you can estimate what it is based on the photon energy density, because if you know the thermodynamic history of neutrinos, you know that their energy densities are related. So if you assume that there's, say, n effective equals 3, so 3 species of neutrino, then you can get rho nu from rho photon. But in fact, there's another way you can do this is, I've talked about matter radiation equality. In that radiation, the neutrinos were part of radiation as well. And we've talked about the silk damping, or this diffusion damping. And that diffusion damping is actually very sensitive to the amount of radiation energy density. So by looking at how much silk damping you see, you actually measure rho radiation. So diffusion damping gives you rho radiation, which is rho photon plus rho nu. And you know rho photon from the CMB temperature, so you know rho nu. Okay, are these all the components in the universe, or is there still one more that I haven't listed? Dark energy, yes. Yes. And so what about dark energy? So at this point, we have basically inferred the energy density in all the components in the universe, except for dark energy. And so what can we do with this? If I can turn this on. The first thing that we're going to say is that dark energy, we don't know how much of it there is at this point, but it only matters at late times. So for example, it's negligible all the way between the Big Bang and when the CMB is emitted. So that's already something. So I can write the Friedman equation. And let me not mess up the coefficients in front. So the expansion rate of the universe is related to the energy density in the universe. And so in there I have rho photon, rho neutrino, rho CDM, rho baryons. I have assumed no curvature, and I have this dark energy. So again, the only thing I don't know in here is the amount of dark energy, but I know that that's negligible all the way from the Big Bang to the CMB. And so what this tells me is that from the CMB temperature and power spectrum, I have inferred the whole expansion rate, h of z, all the way between the Big Bang and the CMB. But what I would like is the Hubble rate today. And the problem is I can't just use this formula, because today lambda definitely matters, and I don't know what lambda is. So what's the next step? The next step is something we haven't made use of in all this part, is we haven't made use of the fact that the acoustic scale, the angular position of the peaks, are very well measured, and this sort of form a standard ruler. So you have this acoustic scale, how far the sound could propagate between Big Bang and the CMB, and that's a certain scale in megaparsec. That's a standard ruler, and I've measured the angle of that standard ruler extremely well with the CMB power spectrum. So the first step, the next step, is to calibrate that standard ruler. And so this sound horizon, this acoustic scale, what is its value in megaparsec? And the claim here is that I can predict the size of that ruler in megaparsec based on just this information. And the reason, again, is that this is the sound horizon. So this is how far sound could propagate between the Big Bang and the CMB. And so really it's speed of sound times how much time I had between the Big Bang and the CMB. Or if I want to be a bit more precise, since the speed of sound evolves a little bit with time, it is the sum of CS of time times d eta between the Big Bang and the CMB. And this I can rewrite as the speed of sound as a function of redshift times dz over h of z. Between, again, the Big Bang and the CMB. So h of z, as we've said, we know it at all redshifts where dark energy is negligible. And so in particular, we know h of z throughout this whole range between the Big Bang and the CMB. And the speed of sound, if it was just photon, would be the speed of light divided by square root of 3. But there's also baryons, and we talked about this baryon loading or this baryon drag effect, which slows down a little bit the speed of sound. So this is also a function of rho baryon over rho photon. But we're in luck because rho baryon and rho photon, we know what they are. So in this integral, I know the speed of sound, and I know the Hubble parameter, so I know the acoustic scale. And so you'll get something of order 150 megaparsec co-moving. Okay, so based on just the properties of the CMB power spectrum and temperature, we've inferred all the energy densities except for dark energy, which allows us to infer the whole Hubble function at all redshifts where dark energy is negligible. And from this, we have been able to predict and compute the acoustic scale, so the size of our standard ruler, the size of those hot and cold spots in the CMB. And so the next steps is to reap the rewards of our hard work and to use the ruler. And so how do we use the ruler? We just measure the angular size of the peak. And this angular size of the peak is basically just the size of the ruler divided by how far it is. Neglecting curvature, so co-moving angular diameter distance is the same as co-moving radial distance, so chi to the CMB. So again, the angle I've measured, RS I have predicted based on all the energy densities which I have inferred. And so the result is I obtain the distance to the CMB. So that's cool. So from just the CMB temperature and power spectrum, if I assume flat lambda CDM, which certainly is an assumption, I have inferred the distance to the CMB. And the distance to the CMB is some integral over the Hubble parameter at all redshifts between the CMB and us. Okay, now, luckily for me, I know the redshift of the CMB. And again, the reason I know the redshift of the CMB is because I can predict the temperature of recombination from first principles, if you remember, with this Saha equation. And I know the temperature today, and so I know the redshift of the CMB is about 1,000. And I know the redshift today because that's 0. So I know the distance to the CMB, and I can relate it to the Hubble parameter. And in the Hubble parameter, there was only one thing I didn't know, one number, which is lambda. So this I can think of as an equation for lambda. So h of z equals stuff I know plus lambda. And the integral of stuff I know plus lambda equals something I know. And so from this, I get lambda. And so with this process, I have actually inferred the energy densities of all the components in the universe, including lambda. And if I do this, then what I have is I have every single quantity in the Hubble parameter as a function of z. And so I infer the Hubble parameter of z at every redshift. And so in particular, I have constrained the whole function, the whole Hubble expansion rate as a function of cosmic history. I can evaluate that function at redshift 0 today and get Hubble today. And so I thought this was a useful exercise when you think about how the CMB constrains the Hubble parameter today versus how the supernovae do it. You can see that it's not super trivial how the CMB does it, but once you think about it, it's understandable. So first, you get all the energy densities in the universe except for dark energy. You get photons from the CMB temperature. You get baryon, matter, neutrinos from other properties of the power spectrum. Importantly, you assume flat lambda CDM, so no curvature. Once you have this, you have the Hubble parameter at all redshifts except where lambda matters. But, so you know everything except for one number, lambda. And this one number you can infer by using your standard ruler. Yes, questions?
So if I remember correctly, at some point you mentioned that CMB has this integrated subscript component.
Has the, say it again?
The integrated subscript.
Oh yes, the ISW, yeah.
Affected the lab scale.
Mm-hmm.
And I think you mentioned that the dependence also in that on that energy.
Yes,
It has a whole component of evolution.
you are right. The amplitude and the scale of the integrated Sachs-Wolf depends on dark energy. And so you might wonder, why can't I just use this to learn about dark energy? And you can, but in practice, the precision to which we can measure the ISW is not great, only a few sigma. And that has to do with the large cosmic variance on large scales. So in principle, if you didn't have this, yeah, ISW would tell you about dark energy.
But if you have like a large enough, like a telescope or a CMB telescope that has a really good large scale.
Yeah, so that's the problem is that cosmic variance statement is, say, you know, if you're mapping the whole sky, which Planck pretty much has, and if you're mapping those large scales to cosmic variance precision, then the signal to noise on ISW will only be a few sigma. So that's a limiting factor. Yeah. There's other ways from the CMB alone that you can infer lambda, and that's, for example, if you add CMB lensing to the mix. So CMB lensing is another observable that depends on the late times, and so it contains information about that lambda. Yeah. Any other questions? Yes.
So is all the information contained on the CMB observable? Would you need like external priors like on the their proportion ratio from the
Yeah, so in this case, you can do all of this from just the CMB. Because, so yeah, you know the photon energy density from the CMB temperature, and you can basically infer the matter density field from those effects. Radiation driving, there's actually the early ISW after CMB actually helps as well, and the impact of lensing. So you don't have to assume the photon to baryon ratio from, say, BBN. You can infer it from the CMB alone. Yes? Yes, right. Because you know that dark energy only starts to dominate around redshift 0.5. And so when you're at redshift 1,000 and above, dark energy, we know, is completely negligible. Yeah. Yeah. Very good point. OK. So this is all I wanted to say about Hubble parameter from the CMB. And in the slides, I'll put a summary version of this in case you haven't had a chance to take notes. And in the last half hour, I would like to tell you about neutrino physics, which I think is another interesting direction for basically using the universe as a lab, so using the CMB and large-scale structure to learn about just basic particle physics stuff. So I may have a bit too much content. We'll see how that goes. So neutrinos are some of the most abundant particles in the universe. They're the second most abundant particles after photons. And yet there's very much we don't know about them. And the reason why we know so little about them is because their mass is very small and their interaction is very weak. It is the weak interaction. And for this reason, there's a number of open questions in neutrino physics. One is, what is their absolute mass scale? And so we know something about their mass differences, or the difference of their squared masses from neutrino oscillation, but we don't know what the overall mass of neutrinos is. We do not know whether they're their own antiparticle or not, and then other questions in particle physics about neutrinos. So there's many particle physics experiments underway, which are aiming to tell us a lot more about the neutrinos, including constraints on the neutrino mass scale, the hierarchy, so how the masses are ordered, and whether they are their own antiparticle or not. But this is a place where cosmology can actually place constraints on these quantities that are competitive and maybe in some cases better than particle physics experiment. So really exciting stuff. And so cosmology can tell us about the absolute mass scale, the hierarchy, whether it's normal or inverted, and whether there are additional neutrino species beyond the three that we know, which are the electron neutrino, the mu neutrino, and the tau neutrino. Because of time, maybe I'll skip this part, but it'll be in the slides. And I'll just tell you about those neutrinos from the Big Bang, the cosmic neutrino background. So just like you have a background of photons from the Big Bang, you have a background of neutrinos from the Big Bang. So this is the cosmic neutrino background. And what you can see is the typical neutrino energies in this background are very low, of order micro electron volts, compared to all of the other neutrinos that you might be hearing about, the solar neutrinos, the atmospheric neutrinos, the ones that are produced in reactors, etc. And the rate of interaction of these neutrinos grows with their energy. And so when you have those cosmic neutrinos that are so low energy, basically their interaction cross-section is extremely small, and so they're very hard to detect directly. And so the cosmic neutrino background hasn't been detected by particle physics experiments, a situation which is often summarized as the cosmic neutrino background hasn't been detected. But I would argue that it's inaccurate. The cosmic neutrino background has been indirectly detected through its effects on the CMB. And in fact, more than just its existence have been detected. Yes, right. That's a really good point, because I imagine, this plot assumes zero mass. Otherwise, everything would be shifted to the right a lot. Okay, and so these are the cosmic neutrino backgrounds, and so the first natural question is, do they matter? How much energy is in these neutrinos? And the answer is they matter a great deal during radiation domination. Once the temperature of the universe has cooled below the masses of the electrons, you have this event where electrons and positron annihilate into photons. And this causes a difference in the temperature of the cosmic microwave background and the cosmic neutrino background, which would otherwise be equal. And so the temperature of the cosmic neutrino background is also an equilibrium spectrum, but at a temperature slightly lower than that of the photons. And if you convert that temperature into energy density, so at early time, and certainly in the radiation era, the neutrinos were relativistic. And so the energy density in a relativistic species is the sum of that in the photons plus that in the neutrinos. And the neutrino energy density is related to the photon energy density. There's this change in temperature, and then there's this factor because neutrinos are fermions, whereas photons are bosons. And this N effective parameter tells us about how many basically neutrino species there are. So really it's mass eigenstates, but let's think about them as species. So I've told you about the electron neutrino, the muon neutrino, and the tau neutrino. And so N effective is 3 in the standard model. And so when you compare these two components of the energy density at early time, you find that neutrinos are actually 40% of the total relativistic energy density. So throughout these lectures, when I've told you about matter radiation equality, radiation was not just photons, it was photons and neutrinos were a big part of the energy budget. And it turns out the CMB gives us a way to measure this N effective parameter by just measuring the total radiation or relativistic energy density and comparing them to the photon energy density, which again we get from the CMB temperature. So in practice, how does that work? How does the CMB tell us about the radiation energy density? So not just the photon, but the total radiation energy density. And this kind of always has to do with timing. So again, here's the Friedman equation that relates the expansion rate of the universe to the energy density. And in this energy density, you'll have not only the photons and matter, but you also have the neutrino. And so basically, anytime you crank up the energy density in the universe, you crank up the expansion rate. And so if you do this, the universe will expand faster. And so for any event that occurs at a fixed temperature, for example, the emission of the CMB, so again, recombination occurs at a fixed temperature. Temperature is just a measure of how much you have expanded or diluted. If I change the expansion rate, all it means is that I'll reach that temperature faster. So if I add energy in the neutrinos, the expansion rate is faster. I'll go from the Big Bang to the CMB faster. And so this basically, what it means is that the neutrinos, for the purpose of the CMB, they change the timing of things. They change how fast you go from the Big Bang to the CMB. And that modifies a lot of the scales in the CMB. For example, one that gets modified is this one, the acoustic scale, you know. How far did the sound wave get to propagate between the Big Bang and the CMB? Well, if your speed of sound is fixed, it's just a measure of how much time there is between the Big Bang and the CMB. And the neutrinos modify this. And so, again, a reminder of a number of the scales we've talked about. The acoustic scale depends on how much time you have until the CMB. The matter equality scale and the damping scale also depend on time. And because of this, we can measure this N-effective parameter. So what I'm showing here, for example, is the effect mostly on this diffusion damping scale, which tells you about the radiation energy density because it tells you about how much time there was for that diffusion to occur. And so through this effect, for example, the amount of diffusion damping, you can measure the number of effective neutrino, and current constraints find the number of 3 with a pretty good precision. And so the fact that this N effective of 3 has been detected to be different from N effective of 0 is a detection of the cosmic neutrino background. So when you find N effective equals 3, you have detected the existence of the cosmic neutrino background. And you might call this indirect because you haven't seen the neutrinos, you've seen the cosmic microwave background. But in that regard, you might call any detection of a particle indirect because you haven't seen the particle, you have seen its effect on your detector. And so the cosmic microwave background detects the existence of the cosmic neutrino background and the fact that there are 3 species of neutrinos. But in fact, it does more than that. It doesn't just detect that there's a mean neutrino background. It actually detects that this neutrino background has fluctuations. And so I'm going to show you again the same animation I showed you a few lectures ago that was trying to illustrate the baryonic acoustic oscillation. And before we focused on the dark matter, whose potential basically just kept growing over time. And we focused on the gas and photons, where you saw that sound wave propagate over time. But this time we can also look at the neutrinos. So first let's focus on the gas photons and the neutrinos. And as I play the video, what you can see is this sound wave propagating in gas and photons. But you can also see the neutrinos are propagating a bit ahead of the gas and photons. So let me play this again. Again, the gas and photons travel at the speed of sound, which is speed of light over √3. But the neutrinos in green, you see a lot of neutrinos traveling faster than this. And that's because your neutrinos, when they're relativistic, actually travel at the speed of light, not the speed of sound, which is speed of light over √3. And so what you're seeing here is that the neutrinos are sort of ahead of the photon baryon plasma. And because you have this component of energy that's traveling faster than the speed of sound, sort of very heuristically, you can think of the gravity of these neutrinos pulling the plasma waves a bit farther than it would have otherwise. And so in practice, when you look at the power spectrum, what this does is it's a shift to the BAO peaks. But watch out that this is an additive shift. So all the shifts are moving to the right by basically the same amount in L. So this is different from changing the acoustic scale, which would be a multiplicative change in the position of the peaks. And so this effect is very unique. It's very much not degenerate with other cosmological parameters. Only neutrinos with fluctuations traveling at the speed of light, or any other particle with fluctuations traveling at the speed of light would produce this effect. And in fact, this effect has been detected. So from just fluctuation only, you have this measurement from Planck. And so what this means is the CMB detects not only that there is a uniform background of neutrinos, it actually detects that there are fluctuations in the cosmic microwave background, and that those fluctuations are traveling faster than the sound waves in the plasma. So there's actually a lot that the CMB can tell us about the cosmic neutrino background. It tells us that it exists, how many neutrinos, so how much energy density, the fact that there are fluctuations, and the fact that these fluctuations propagate in the way we expect for neutrinos. Okay, so this was from the CMB alone, what we can learn about neutrinos. And so again, the amount of neutrinos, the energy density, the existence of fluctuations, and how they propagate. Another important properties of neutrinos that we would like to learn about that we currently don't know is the masses of the neutrinos. What this diagram is trying to visualize is for the three mass eigenstates, so the three neutrinos, we do not know their overall masses, but we know the differences in the squares of their masses through an effect called neutrino oscillation that has been measured by particle physics experiments. And we know that there's a large difference and a small difference. We just don't know in which order they are. And so these two different orderings are called mass hierarchies. And so we don't know if the hierarchy is so-called normal with two low mass and one high mass neutrino, or if it's inverted with one low mass and two high mass neutrinos. And on top of this, because we only know the differences, we don't know the overall mass scale of these neutrinos. And so being able to answer the question of which of these hierarchies is the correct one and what are the actual masses would be a really important contribution from cosmology. So how does cosmology tell us about those masses? The kind of masses we're thinking about, just to give you an order of magnitude, are numbers like this. Of order less than an electron volt. And if you remember, what was the temperature of the CMB when it was emitted? Yes? 3,000 Kelvin. And I don't know if you remember from the first lecture, what's the rule of thumb for how many EV in a Kelvin or how many Kelvin in an EV? Right, so one EV is about 10 to the 4 Kelvin. And so 3,000 Kelvin is a bit less than an EV. And so for these low masses, basically what you find is that the temperature of the universe before the CMB and all the way to the CMB was basically higher than these masses. And what that means is that the neutrinos were actually mostly relativistic before the CMB. And so, right, so the temperature at the CMB, is quite a bit larger than these masses. These masses will basically have no effect on the CMB. And so the CMB alone cannot tell us much about the masses of these neutrinos. And so if you want to see the masses have an effect on cosmology, you need to let the expansion reduce the temperature of the universe up to the point where the neutrinos become non-relativistic. So up to the point where the temperature of the universe is less than the mass of these neutrinos. And typically for neutrinos of order 0.1 electron volt, like the ones we're focusing on, this happens at redshift about 100. So from the history of the universe, the Big Bang all the way to redshift about 100, your neutrinos are basically relativistic, which means their masses doesn't matter. And if their masses doesn't matter, it has no big observable effect that we can observe. But at redshift lower than about 100, their masses start to matter, and this is when we can hope to detect them. And so what does it mean for their masses to matter? Well, when the neutrinos become non-relativistic, they start behaving like normal matter as opposed to radiation. And so what the neutrino mass does is it enhances the matter energy density at low redshift. And this parameter, F nu, is the fraction of the energy density in neutrinos versus the rest of the matter. And a number you can keep in mind is that for the typical, the minimum mass of the neutrinos, you'll find that this fraction is about 0.5%. So, okay, what I'm trying to say is at late times, neutrinos are a fraction 0.5% of the matter energy density. And so if you want to measure the masses of the neutrinos naively, you would need to measure the matter energy density to 0.5% precision. And one way you can do this, again, is by measuring the expansion history of the universe. And so things like baryonic acoustic oscillations in galaxy surveys. If you can measure this to about 0.5% precision, you'll be able to tell that the neutrino energy density, which is a fraction 0.5%, is there or not. But there's another effect beyond just the expansion history, and it's an effect on the growth. The way this works, as I mentioned several times throughout the lectures, the growth of structure is a competition between two things. One is the expansion of the expansion of the universe, which tends to flatten the density fluctuations. And the other one is the gravity from the matter that collapses, which tends to deepen the potential. And so whenever the component that dominates the universe contributes equally to the expansion and to the clustering, the gravitational potentials stay constant. But if you add a component that contributes to the expansion and not the clustering, then the expansion will win and you will lower the clustering of the rest. And so this is exactly what neutrinos do because they have free-streamed and erased structure. They have contributed to the expansion of the universe, but not the growth of structure. And so when you look at what the effect on the matter power spectrum today, with neutrino masses versus no neutrino masses, what you see is that on most of the scales we observe with galaxy surveys, the power spectrum has been reduced. And something that's helpful and not obvious is that that reduction actually is not proportional to how much energy is in the neutrinos, but it scales as that times how much expansion has happened. And that gives you an additional large factor which enhances the effect. So again, to summarize, once the neutrinos are non-relativistic, they change the energy density of the universe by 0.5%. And so you can detect that if you measure BAO to 0.5%. But they also change the growth of structure by a much larger amount, 4%. And so if you can measure this reduction in the matter power spectrum, that's 4% in size, you'll have detected the masses of neutrinos. Okay, so I think that's all I wanted to say about those neutrinos today. And so again, the existence of this cosmic neutrino background has been detected by the CMB. In fact, it's true by the BBN as well. The CMB detects not only that there is a cosmic neutrino background, it also tells you how much energy is in this, and therefore how many neutrinos there are. And then not only that, it also tells you about the fluctuations in the cosmic neutrino backgrounds and how they propagate faster than the sound speed. And then cosmology can also tell us about the masses of the neutrinos through their effects on the total energy density, which changes the expansion, and also through their effect on the growth of structure. Okay, so this is really all I wanted to say about the cosmic neutrino background. And I think this is pretty much all I was hoping to tell you all today or this week throughout these lectures. So again, a quick summary. All the slides will be on the Google Doc that's linked from the website. I think the first 4 lectures are on it, and I'll be adding the 5th lecture today. So we talked about what the CMB is, what the mean properties of the CMB are, temperature, spectrum, the physics of recombination, that part of thermal history in the universe, the very rich physics in the temperature fluctuations of the CMB, the also very rich physics of the polarization fluctuations in the CMB. I think there's really, I've covered a lot in those lecture 2 and 3, and so please don't get alarmed if a lot of it didn't make much sense. I think that's something that's worth revisiting and just spending time with Wayne Hu's tutorials, animations, and with the various textbooks that I linked. I've told you a little bit about the secondary anisotropies of the CMB. So what happens between the large-scale structure, the less scattering surface and us, and how these are contaminants if you care about the early universe, but they're also an amazing source of signal and information on the large-scale structure. I've shared with you my limited knowledge on how CMB measurements and CMB instrumentation works, and given you just 2 examples of really timely and important things we can learn about the universe from the CMB, so the Hubble parameter as well as physics of the neutrinos. And so I just wanted to stop there and thank everyone here, really the organizers, for having me and taking such good care of all the speakers and all the students. All of my colleagues here with whom I've had a really good time and learned a lot from conversations. And finally, all of the students for all of your attention, your enthusiasm, the amazing questions, which have stumped me a few times and from which I have learned. So thanks a lot. So I'm a bit early, so if there's questions, I'm happy to take them, of course.
Thanks for the lectures. So I know we talked a bit about this yesterday, but could you comment on the pros and cons of having a CMB experiment in space or on the ground?
Yes, thank you. That's a really good question. And so today, the only part I mentioned was the atmospheric transmission and the atmospheric emission. And so from this perspective, it's better to be in space than on the ground because you don't have to look through the atmosphere. So that's one thing. The other thing is that I didn't mention is when you're in space, you don't have issues like emissions from the ground. So when the ground is very hot, it's at room temperature, 300 Kelvin. And so it can emit light that will go into your telescope, or it can emit light that reflects on the atmosphere and then goes onto your telescope. So that's that. The other advantages of being in space is it makes it easier to scan the whole sky, as opposed to whatever portion of sky is easily accessible from the ground. So from this perspective, if you can go to space, go for it. The challenge, of course, when you're trying to send an experiment to space is that it takes a very long time, it's very expensive, and typically your telescope will have to be smaller because it needs to fit on one of those rockets that shoot them up there. And so when you have a ground-based experiment, the advantage, other than being cheaper and being able to move on a faster time scale, is you can have much larger apertures. You can have sort of more latest technology of detectors. And that's important. So with that large aperture, for example, for experiments like ACT, South Pole Telescope, Simon's Observatory, you're able to get a very high resolution, which would be difficult or impossible to do with a smaller telescope. So that's one of the big trade-offs. And so for this reason, there's like a big complementarity between the ground experiments and the space experiments. And I think generally in astronomy, the philosophy about ground versus space telescopes is if it can be done from the ground, do it from the ground, because it'll be a much easier, faster, and cheaper. And do from space what you can only do from space. And so in that case, in the case of light bulb, for example, these are the largest angular areas and the many, many frequency bands which let you control foregrounds. Thanks. Any question there?
So you told that the telescopes today have a great resolution, and we don't need to improve on that. But
I don't know that I said that second part.
but we measure polarization modes, and we didn't measure primordial beam modes. So what's getting on the way?
Right. Yes. So first of all, I would agree with you that the resolution of current experiment is really nice. This order arc minute beam is what lets us observe, sort of resolve individual galaxy clusters or galaxy groups in the scale structure. And so it helps with a lot of those secondary anisotropes, and it helps with lensing. And lensing is important also when it comes to B modes. Now, I wouldn't say that we don't need a higher resolution for CMB experiments. I'd be very happy to have a higher resolutions. There's a lot to learn, especially about the secondary anisotropes on much smaller scale. So that would be great. And then I think the second part of your question was about the primordial B modes and why haven't we detected them yet? And I think there's several elements to answer this. One is there isn't a target from inflation for how large the B-mode power spectrum should be. So we do not have a predicted number for this is the amount of B-modes you should see. So it is also possible that the amount of B-modes present are inexistent or so low that we will never detect them. That's a possibility. But another possibility is that the signal is there waiting for us to detect it just at a bit lower noise levels. And so in this search for B-modes, a big part of the approach is to try to always lower the noise level of the maps you're making on large scales, where the B-modes are. And an equally important part is to control your foregrounds, to lower the level of foregrounds in your map to similar levels. And that's really hard. So on large scales, those foregrounds are mostly from our own Milky Way. And so you need to understand the structure of the dust and the radio emission from the Milky Way very, very accurately. So that's difficult. And then another challenge is that the dominant part of our actual B-modes at the moment is due to lensing of E-modes. And so we talked yesterday, I think, about how we can do delensing to try to remove this lensing, but that's also a challenging part. Thanks for your question.
Thank you very much for the lectures. So, yeah, the neutrino masses, they suppress the power on small scales, right? Which is easily seen in the matter power spectrum. Does that also produce a recognizable pattern in the CMB power spectrum, or does the CMB is more sensitive to the neutrino's energy density per se, not exactly its masses?
Right. Yeah, so thanks for the question. I went a bit quickly over this. So, right, again, the CMB was emitted at a temperature of about 3,000 Kelvin, which, as we said, is something like 0.5 electron volts. And so if the neutrino mass was higher than 0.5 electron volts, then the neutrinos would be non-relativistic by the time of the CMB. Their mass would actually matter, and the CMB would allow us to detect their effect. The fact that we're not detecting their effect on the CMB alone means that their mass has to be less than 0.5 eV. And in this scenario, then yes, those neutrino masses have no effect on the CMB alone. One way in which what I said is not quite accurate is they do not modify the physics of the universe before the CMB, but they can change the expansion between the CMB and us, so they can have an effect on the distance to the CMB. And so that's the only way in which the primary CMB is sensitive to neutrino masses of such low values is via the distance to the CMB. Now, there's other observables from the CMB that are not just the CMB that are sensitive to those low neutrino masses, and CMB lensing is a really important one of them. Okay. So CMB lensing probes a mix of growth of structure at late time and expansion history at late times, which are both affected by neutrino masses, even very small ones. Yeah. And so, yeah, they're a promising way to measure the neutrino masses.
Yeah, and I assume that this effect on the distance to the less scattering surface is degenerate with dark energy, for example.
Right, yeah, so yeah, anything that's just the distance to the CMB will be degenerate with the other parameters that modify the angular distance to the CMB.
Yeah, so it might not really be a good
energy,
probe for
curvature.
Because of the degeneracy. Yeah, thanks. Thank you very much.
Thank you for your lectures. So I was thinking about the Hubble tension, and I don't know, I don't really understand the supernova, and I don't work with that, but whenever I study CMB, it seems like it's so great. I mean, our measurements are very good, and the fitting, it seems very good as well. So whenever I'm learning about this, I keep thinking that perhaps we should understand better the astrophysical properties of supernovas and all other estimates we have. And I tend to think that, I don't know, CMB is the correct one. But also, I guess we kind of assume a lot of things about the model when we're doing this fitting. So I'd like to know what you think about that.
Right. No, thanks. That's a really good question. I think it's a question that a lot of people are wondering about. You know, what is the solution to this Hubble tension? So I'm not at all an expert in the supernova side, so I'm not really qualified to say, you know, how much I should believe them or not. On the CMB side, one thing that's important to note. So yeah, there's those two things. So one is the physics of the plasma between the Big Bang and the CMB is plasma physics at fairly low energy. It's stuff that we understand really well, sound waves, linear waves because they have such a small amplitude. So the physics is extremely clean and well understood. So in terms of modeling, that part is easy. Observationally, it's still a challenge to measure the CMB power spectrum with such accuracy without systematic effects. So that's one thing to keep in mind. And the other one is that, as I've tried to explain, the way we measure the Hubble parameter today from the CMB is that we don't really measure the Hubble parameter today. We just infer all the energy densities at all times, and we use that to predict the Hubble parameter today. And so, like you said, there's some model dependence in the sense that there's a big lever arm between inferring those energy densities at redshift 1,000, and then assuming that everything is okay and I can extrapolate all the way to today. So that's a strong assumption about lambda CDM, and in this case, you know, flat lambda CDM. And so, you know, in terms of solutions to the Hubble tension, it could be that the CMB is a bit wrong, the supernova are a bit wrong, both are a bit wrong, or the thing that I think most theorists are hoping for, neither of them is wrong, and there's some interesting new physics that makes them both agree. But, yeah.
Okay.
Thanks for your question.
And just, I guess, a simpler question, because I was wondering, when you were saying about the B modes, the E modes, and the T, of course, the temperature, I kind of understand what we want to see when we get this power spectrum, but I don't actually get what we get from the TE mode.
Cross correlation, right. So you could ask, you know, what's the point of measuring the TE power spectrum instead of just TT and EE? So I think the first naive answer is there's a non-zero signal there, and so, you know, why not measure it? Especially once you reach the cosmic variance limits, that means your measurement error is smaller than just the variance due to the fact that you have a finite number of Fourier modes. Then you definitely don't want to leave information on the table, so let's measure everything. But then there are things for which TE is particularly useful. And one is there's a number of observables that have to do with the acoustic peaks of the CMB. So, you know, what's the angular scale at which they occur, the odd versus even height asymmetry, the effect of lensing, which smears the peaks. And as I've tried to outline in the polarization lecture, the TE power spectrum oscillations are a bit sharper in TE than they are in EE. You have this change of sign. And so for things like lensing, which smears the peaks, or for things like an effective that cause an additive shift to the position of the peaks, it's really helpful to be able to measure those sharp peaks from TE. And so that's one place where it's particularly useful to have TE.
So it's like it's less sensitive to those things, the TE mode is less sensitive to the lensing and
no, sorry, I was sort of trying to say the opposite, that by having those sharp peaks, the effect of ineffective and lensing and baryons was very visible on these sharp peaks.
Okay.
In practice, T is very well measured, but yeah, so I was basically trying to say there's a lot of useful information in TE. Yeah.
Okay, thank you.
Thanks.
Hi, thank you for the lecture. I actually have a question for neutrino, and I also work on CMB, I work on SO, and I feel like when I talk to people working on neutrino physics, they don't really take these constraints from cosmology seriously. For example, like the latest constraint from DICE this year is a big news for our community, but it's not like the same for them. Like, can you comment a bit on this?
That's a good question, and I guess so. The question is about how does the interface between cosmologists and neutrino physicists work, and what do neutrino physicists think of our constraints from cosmology? I guess.
Yeah, I think so.
And I think that's a good question. I think in part it's probably a sociological question of how much we communicate with each other and how we communicate our results. I think it's fair to say that for a particle physicist, you might consider all of our particle physics measurements in cosmology to be very indirect and in some ways model independent. And so I think that's always a fair concern. And of course, we have a number of systematics that are astrophysical. And so maybe contrary to a particle physics experiments where if you're not happy with it, you can build a better one. For us, some of our foregrounds are the way they are on the sky, and they're a limiting factor. Maybe my personal opinion might be as well that the bar we set for ourselves in terms of claiming detections or hints, we might benefit from having a high bar there if we want people from outside our field to believe us. And so, for example, statements about anomalies or the minimal mass hierarchy being ruled out at 2 sigma might be statements we might want to be careful about when 2 sigma is not something that perhaps a particle physicist would consider significant, and for good reasons. And so I wonder if part of it has to do with how we communicate our results to the rest of the world. And perhaps if we put our upper limits on the mass of neutrinos not as a 90 or 90% mass confidence, but as a 5 sigma mass that we rule out, I think it might help us be more trustworthy to our colleague, and it might cut some of the noise in overstating our results.
Okay, thank you.
Thanks.
We could also have questions at the Q&A.
All right. Maybe the last question.
Thanks for your lecture. I just want to ask a question about the parameter estimate, because just now you say we can extract the cosmology parameter from the power spectra, then we can use the theta as a standard ruler to constrain the lambda. This is the same step we do, or we do the first step, then we do the second step?
Sorry, can you repeat the last part of the question?
If we, first step, we estimate the parameter from power spectra, then we get the result of theta h, then we use it to constrain the, as a standard ruler to constrain the lambda, or we do this together?
Yeah, yes, thank you. No, thanks a lot. That's a really important question, and something I should have probably clarified. So in practice, the way you analyze the CMB data is you measure your power spectra, and you have theory curves for what the power spectrum should look like, depending on a given choice of cosmological parameters. And then you fit for the cosmological parameters based on the power spectrum you see, an approach very similar to what David explained earlier today on how you fit to a power spectrum. And so in practice, what you do is you have Boltzmann codes, which for each value of your cosmological parameters predicts the power spectrum. And then you have a likelihood, which then tells you whether that prediction is a good match to your data or not. And then with this, you have priors on your cosmological parameters, and what you're trying to do is to basically plot the posterior function on your cosmological parameters. And because it's a high-dimensional parameter space, the way you explore the posterior is typically with things like Monte Carlo Markov chains. So in practice, when you do your CMB analysis, you're fitting for cosmological parameters, maybe 6 or 7 of them, plus a bunch of nuisance. And you fit to the power spectrum, and you get posteriors on the cosmological parameters. And with these posteriors, you can now predict H naught and propagate the uncertainty. So in practice, you're not doing these things, in this order or in any order. This happens sort of under the hood in your MCMC chain. So you're not, first measuring these observable separately, the scale, the peak ratio, getting those numbers, predicting the acoustic scale. This happens sort of automatically inside your likelihood expression.
It's also in same time, I also estimate the lambda.
Say it again.
So when you say we use the power spectra, the likelihood so the result we already can obtain the lambda.
Yes, so you can make different assumptions. For example, you can try to fit your CMB power spectrum within flat lambda CDM or with it non-flat lambda CDM. And so this sort of heuristics for how you get H naught I showed here was in the case of flat lambda CDM. And so in that case, by assuming that there was no curvature, there was no more geometric degeneracy, and so lambda could be constrained directly. But if you relax the assumption that there's no curvature, then you get this degeneracy.
So in this case, we don't need to use a standard ruler?
So in that case, you will need something else. if you want to break that degeneracy to obtain the I guess H naught. And you can break this degeneracy in various ways. Usually it's by adding late time information, so whether that's baryonic acoustic oscillations or CMB lensing or something else.
Okay, thanks.
Yeah. Thank you.
Okay,
Great.
let's
Thanks a lot.
thank
Thank you.
Emmanuel again.